Friends, in this video you would learn about the work done in rotating a dipole when placed in a uniform electric field, and thereby we will derive the expression for the potential energy stored inside a dipole when it is placed in any uniform electric field. So friends, whenever a dipole is placed in any electric field, now the question comes, what is a dipole? Now, dipole happens to be a combination of equal and opposite charges separated by any small distance. Let's call this distance as 2L. Now friends, dipole is not defined in terms of charge or distance. Rather, dipole is defined in terms of a physical quantity which is called as its dipole moment, and the dipole moment is always a vector quantity whose direction is from a negative charge to a positive charge. So what I am doing, I am showing you this dipole moment by the help of this purple colored arrow, and the magnitude of the dipole moment is P is equals to Q into 2L, where Q happens to be the magnitude of any of the charge, any charge, whether positive, whether negative. We are not interested in the nature, we are not interested in the sign, magnitude of charge, and 2L happens to be the distance of separation between the two charges. Friends, if you haven't watched my videos on electric dipole, electric field due to dipole, or torque experienced by a dipole when placed in electric field, I would ask you to click on the top right hand corner on the I button and you would get the link of the same. So friends, every dipole is defined in terms of this dipole moment, and as I told you, dipole moment is a vector quantity, so its direction is directed from a negative charge to the positive charge. Now whenever a dipole is placed in electric field, it used to experience a force. The amount of force experienced by any charge in an electric field was equals to QE. So this is also force QE on a positive charge, and this is also force QE on the negative charge. What happens to these forces? The direction of these forces are different. You can see in case of positive charge, the direction of the force happens to be along the direction of electric field, whereas in case of a negative charge, the direction of the force happens to be in a direction opposite to that of electric field. Now both the forces are equal in magnitude, but their line of action, what is the line of action? A line that happens to pass parallel to the forces. So this happens to be the line of action of this charge, line of action. So this happens to be the line of action of this particular force, and this happens to be the line of action of negative charge, so this particular force. Okay, now you can see both the dipole are subjected to two equal and opposite forces, but their line of actions are different. Now when a body is subjected to two equal forces whose line of action differs, then the body starts experiencing a torque. Now friends, the expression of torque we have already derived as torque is equals to PE sin theta. If you haven't watched that video, click on the top right hand corner I button and you would get the link. Go and watch that video, friends. So whenever a dipole is placed in an electric field, it always starts experiencing a torque. The expression of the torque happens to be P cross E in vector form, or torque is equals to PE sin theta. Now friends, under the action of this torque, our dipole tends to rotate inside the electric field. Now whenever rotation occurs under the action of some sort of torque or some torque, then the field does the work. So here what you can see, this particular, under the action of this particular torque, let's say if our dipole gets rotated by a small angle d theta, then the amount of work done by the field will be dw is equals to tau into d theta. So if it gets rotated from some initial angle theta I to some final angle theta f, then the total amount of work done can be obtained now by integrating torque d theta from the limits of theta I to the limits of theta F. So I am putting up with the limits over here as theta I to theta F, because I am assuming that my dipole gets rotated through an angle of theta I to theta F. Now, what is the expression for torque? You can always substitute the expression of torque from here. Can you see? So I have done into this, and my expression now looks like Pe sin theta d theta, and I am rotating the dipole from some initial angle of theta I to some final angle of theta F. Now friends, this Pe can be taken outside of this integral as they are constant. So the expression would look like work done is equals to Pe integration sin theta d theta, and the limits of integration being theta I to theta F. So now friends, what will be the integration of sin? Integration of sin theta happens to be minus times of cos theta. So those who are not aware of it, please note it down. Especially those who have opted for biology or biology students should take care about this integrations. So integration of sin theta will be equal to minus times of cos theta. So substituting it over here, for integration sin theta d theta, the result will be work done is equals to minus Pe cos theta with the limits of integration being theta I to theta F. I have taken this minus sign here from here to outside of this bracket, friends. Now, friends, whenever some work is done by the field, that work done by the field is always responsible for change in potential energy. So work done by the field, in this case the electric field, so work done by the electric field will be equal to the change in potential energy. Now remember friends, I am just giving another example over here. Suppose this is the ground and a ball is kept at some height h from the ground, isn't it? So what will the potential energy of this ball? That happens to be mgh, and let allow this ball to fall onto the ground. When it reaches onto the ground, the potential energy of the ball happens to be 0. So what will be the work done by the field? Which field we are talking about? The gravitational field. So work done by the gravitational field will now be equal to change in potential energy. So work done by the gravitational field will be equal to change in potential energy. What is change? Change in physics always means final potential minus initial potential. So what is the final potential? The ball is finally on the ground, so final potential being 0. What is the initial potential? Initial potential being mgh. So 0 minus mgh. So what is the work done by the gravitational field, friend? That happens to be minus mgh. So that happens to be minus mgh. Now this is the work done by the gravitational field. Now remember friends, whatsoever the work is done by the field, that is always equal to minus times the work done by the external agent. So that's the reason why you know that work done by the agent is minus times the work done against any conservative field. In this case, it is the minus times the work done by the electric field. In this case, it will be the minus times the work done by the gravitational field. So work done by the agent. So here if I am interested in finding out the work done by the agent, so that work done by the agent will be equals to minus times the work done by the field. Which field we are talking about? In this case, it is the gravitational field. So minus times of minus mgh, and that happens to be plus mgh. So that is how you find out the work done by the external agent. This is the work done by the agent, and this happens to be the work done by the field, friends. So please take care about this fact. Now here, the dipole gets rotated under the action of the torque applied by the field. Now this torque acts in the clockwise direction, and how much is the torque acting? That torque was Pe sin theta, and under the influence of this torque, our dipole gets rotated by some angle from theta I to theta F, and in this process the field does some work. What is the work done by the field? And that happens to be minus Pe cos theta, limits of integration theta F to theta I, lower limit to upper limit. Substituting the upper limit and lower limit in this expression, I will get as work done by the field. Here I am writing down, friend, work done by the field is equals to minus times of Pe bracket open cos theta upper limit minus cos theta lower limit. Is this okay? Any confusion to anyone? So work done by the external field or work done by the field happens to be minus PE cos theta final minus cos theta initial. You should always remember the conservative forces or the conservative field always tries to reduce the potential energy. They try to bring the potential energy down. Is that clear? So this is the work done by the electric field in rotating the dipole from theta I to theta F. Let's substitute it over there. So this is the expression I've got, work done by the field. Now let me rewrite it. Work done by the field happens to be minus PE cos theta final minus cos theta initial. Now as I told you, work done by the field is responsible for change in potential energy, and this change is always loss in potential energy. So change in physics always means final potential energy minus initial potential energy. Let's substitute that. Final minus initial minus PE cos theta final minus cos theta initial, opening of the bracket. So on comparing both sides of the equation and opening up the brackets, the potential energy final minus potential energy initial is equals to minus PE cos theta final, and this minus and minus combined to give me plus PE cos theta initial, comparing final with final and comparing initial with initial. So on comparing these two, I would get the equation for potential energy final as minus PE cos theta final and potential energy initial as minus PE cos theta initial. This is the minus, and this taking the minus on the other side or multiplying the equation by minus 1, minus PE cos theta initial. So in general, I can say that the potential energy of a dipole when placed in any electric field happens to be minus PE cos theta, or I can say that in vector form, potential energy being equal to minus P dot A. So that was the expression that we have derived for potential energy of dipole when placed in electric field, and the expression happens to be minus PE cos theta, or in vector notation it is minus P dot A. Friends, solve the numerical problems from your textbook, and this finishes off the topic on electric potential and potential energy. If you haven't watched all other topics, please click on the I button. You will get the playlist of potential energy. Watch all those videos also. That will give you a better knowledge about potential and potential energy in electrostatics, friends. Friends, thank you for watching. Don't forget to give a like or comment. अगर अभी तक आपने मेरे इस चैनल को सब्सक्राइब नहीं किया है तो please do the same. Don't forget to hit the bell icon so that whenever a new video is loaded, you get the notification. Take care, and we will meet back again with a new video and a new solution. Thank you, friends.